I'm Stephen. I'm a grad student at Stanford. I work with Stephen Boyd on convex optimization and various applications and tools. And I'm going to be talking about this package CVXPY that I developed and have been working on for a while. So first, let me introduce convex optimization. A convex optimization problem has the following form. You have some variable x that you're solving for, some decision variable, and you have an objective function that, let's say, you're minimizing, f naught. You have inequality constraints where these functions fi of x are less than or equal to 0, and then you have linear equality constraints. And in addition, you have the restriction that all these functions, f naught through fm, are convex. And so there's a formal definition of convexity here, but essentially it means that they have positive curvature. They curve upwards, right, like a parabola. And this is a very interesting, so this is a restricted class of optimization problems, a restricted class of optimization problems. There are, an infinite number of non-convex problems. But this turns out to be a very useful restricted class to consider for many reasons. One reason is that you have very elegant theory explaining how to analyze these problems, algorithms that can be used to solve them efficiently, how to guarantee that you've achieved the solution of the problem, how to analyze things like the sensitivity of the solution to the constraints and things like that. There's all kinds of work that's been done to develop this system, this framework, and make it as useful as possible. And corresponding to that, you have an enormous amount of really, really high quality software that's been developed to solve these problems. And it's very robust, it just works. You can plug in almost anything that fits the form that these solvers require, and it'll give you the solution. And an interesting fact is that, again, this is a restricted class of optimization problems, but it turns out that it applies to essentially every field that we've looked at. Machine learning statistics, this is a major application, or at least it was before deep learning, but all the classical machine learning algorithms are based on convex optimization. So things like SVM, all the regressions. Control, this is a massive application. So a good example is the SpaceX rockets, the landing. It's more or less just convex optimization. There was actually somebody in our group who wrote that. Signal and image processing, medical imaging, scientific imaging, these are major areas where you are, say, reconstructing a volume or something from measurements using optimization. Networking, so optimal flow problems. Engineering design, you could think of things like designing circuits or laying out circuits. There's interesting applications there. Finance, I'm going to show an example later of how you use this for finance. Many, many applications across many, many fields. Okay, how do you solve these problems? Well, there are different ways. One is to use someone's standard solver that's been developed for a particular form of the problem. And examples of these standard forms that you might have heard are linear programs, quadratic programs. A more specialized one is second-order cone program. There are many. But essentially, this is some particular subset of convex problems that somebody has taken out and maybe developed a particularly effective algorithm and package to solve these problems. And then the benefit of having this is that many problems can be converted into these standard forms. And so it's worth investing a lot of effort in these solvers because that's amortized across all these different use cases. And so this is where the really high quality solvers have come from. Now, another method is to write a custom solver for your particular problem. And this you might do if you have a super large problem or you have some special structure that's not going to be exploited by a standard solver. And this is obviously more effort, but if you have particular needs, Real-time constraints, that'd be another example. This can be worth it. And then the third approach, which I'll be talking about, is to use a modeling language. And this sort of gets the best of both worlds in the sense that you don't have to worry about mapping into one of these standard forms, which can actually be quite far from the original problem that you started with. It's not necessarily obvious at all how to arrive at these standard forms. It can require a lot of expertise. And even if you do know how to do it, it's a very tedious and error-prone process. So this automates this for you, just like a compiler will automate the translation into, say, assembly, right? It's the same idea. And so it allows you to write things at a high level that follows the mathematics, and then it will automatically translate it into one of these standard forms. And it can make decisions about what standard form is most appropriate, right? Just like a compiler has optimization decisions it makes. So this comes from a long tradition of modeling language. There's a long tradition of these modeling languages, going back to things like AMPL and GAMS in the 80s. More recently, there's been a number focused on convex optimization in particular. CVX is a big one in MATLAB, and that was the inspiration for CVXPY. They're sort of very similar, especially on the surface. And the function of these modeling languages for convex optimization is twofold. One is to verify convexity, sort of like type checking, and the other is to convert it into the standard form. So the way convexity verification works is through something called disciplined convex programming. So this is like the type system. And it's not too complicated. Basically, you view your functions as expression trees, right? Everything, your objective, your constraint, everything is an expression tree. And then you try and determine the curvature of every node in the expression tree using some very simple rules, in fact, just one rule. And in some cases, this will fail. It'll be indeterminate what the curvature is. That means basically that you have a type error, right? You're not allowed to do that. And so you have to think a bit about how to express your problem using primitives that we provide. So the expressions are formed from variables, constants, and parameters at the leaves, and then a library of functions with a variety of properties that we have enumerated. And these are provided. You can't define new ones. You can contribute to the library, but otherwise you can't, there are no user-defined functions. And that's what makes this like a well-organized and effective system. So this is the basis of the different convex modeling languages. If you want to learn more about the rules, there's this website, dcp.stanford.edu. It's pretty fun if you're into this. Well, let me talk now about CVXPY itself. So CVXPY is a modeling language developed in Python for convex optimization. I started it about 4 years ago when I first started working with Stephen Boyd. It uses disciplined convex programming as well as certain analysis of things like the signs of expressions, and there's a bit more now, but that's essentially what it looks at, signs and then curvature, to verify convexity. It's open source. All the way down to the solvers. So it itself is not a solver. That's an important clarification. It's a modeling framework, but it connects to many different solvers, including many open source ones. It supports some interesting features, like one I'll talk a little bit about is parameters. So these are symbolic constants that you can modify after the fact, and that can be useful for a variety of reasons. It mixes easily with general Python code. I'll show more examples of that. I think this is a big advantage that we get from being in Python versus in MATLAB, for example, where this kind of thing is a bit more difficult. And it's been used in many different areas, different research project classes, companies, certainly thousands of people. It's hard for me to tell, but there are a lot of issues that they post, so there must be a lot of users. There are a variety of solvers that it uses. It comes with 3 open source solvers, ECOS, SCS, and OSQP. I'm not going to say too much about this. Basically, different solvers have different strengths and weaknesses. They handle different problems in some cases. And it's useful to support many different solvers and to give people the ability to plug in their own solvers. And again, CVXPY is not a solver. So you can't say CVXPY didn't solve my problem. You can only say the solver didn't solve my problem. here's what CVXPY looks like. So here we have some sort of weird regression problem, so some sort of lasso problem with constraints. So you have this ax minus b least squares term, right? So that's just a linear regression term. And then we add on this penalty of the absolute values of x, the sum of the absolute values. So this is encouraging sparsity, meaning encouraging entries of x to be 0. Then we have some other random constraints, like the x sums to 0, and the largest absolute value of x is no more than 1. And this doesn't represent anything particular. It's just a convex problem. And here's what the code looks like to express this problem. So note how similar it is to the math. So here you declare a variable. So you have this variable functions, or variable constructor from CVXPY. You give it a dimension, n, that creates this assign, then that's assigned to the name x. You have this sum squares function here. This is one of those predefined functions in the library, right? This is not a user-defined function. This is predefined. And that's applied to a times x minus b. A and b would be numpy arrays. We've overloaded times, minus, plus, et cetera, all that stuff to construct expression trees. And then here's the L1 norm term, which is using a CVXPY function multiplying by some float. And then again, they're added, operator overloading. So then we get this expression tree, which is assigned to cost. It represents this term. Then we make an objective out of that with this minimize constructor. Then we have constraints, which is just a list. We have, again, more predefined functions, and then we've overloaded these rel ops to construct constraint objects. And then we construct a problem with an objective, constraints. We call .solve, and that returns the optimal value and then populates the .value field of the variables with the solution. And so I think it's worth dwelling on this .solve. Like, this is it, .solve, that's the whole thing. You don't say which algorithm it uses, you don't say what hyperparameters it uses, there's no learning rate, there's nothing like that. You just do .solve and then it works, right? Because the problem is well defined, like it's known how to solve these problems very well. And this is really the primary benefit, I would say, of convex optimization. It's that you can just focus on what you're trying to solve and not how you're trying to solve it, right? For many of these non-convex problems, the two get intertwined, right? Because you end up in cases where the method you use will change the solution you get. And that becomes very, very confusing, and I think can really make it much harder to actually address the real problem you're trying to solve, whatever that may be, the real application. Okay, here's an example of mixing Python code with CVXPY, so just generic Python code. So first, a little bit more about parameters. So parameters are symbolic representations of constants. And so they have known sign, shape, etc. And here we have a for loop where we assign various values to this parameter gamma, and we iterate over this for loop, and we call the solve function, the solve method, and we get the result. So we're just iterating, right? We can also approach this in a parallel way. I won't go over this too much, but essentially we have this is using a basic multiprocessing library from Python. You could use whatever you want. This is just a basic one that fits on a slide. We have this function that does the same thing as the loop. We map it over this array of values for gamma, and then that's it. So that's parallelism. And this is a little numerical example solving a lasso problem. And so we have 100 different values of gamma. We want to do a trade-off curve. So right, you have this parameter gamma, this hyperparameter, and you want to see how the solution changes as gamma changes. And just to summarize this, you can see that you do get some advantages to parallelism. It's not perfectly parallel, it's not linear, but there's some benefits here even with this one slide implementation of parallelism. And so this is a nice example of mixing other Python libraries with CVXPY, and I'll have some more examples later. So now an example, something you can go and try out at home. So portfolio optimization. How do you want to buy and sell some stocks? How do you do it? You got some tips. How do you exploit them? So this is how it works. This is what people actually do, more or less. So you have variable W, which is your allocation among your portfolio. So this is like what fraction of your assets are you investing in each stock. And then you have this vector mu, which is basically if you saying whether you think a stock is going to go up and down in value, right? It would be positive or negative, more or less. And then you have this matrix sigma, which is, so you can think of it as a covariance of the returns of the stock. It's essentially just some measure of the risk, right? It's stopping you from investing everything in the stock you think is going to go up the most. And then we have some other constraints that the allocation sums to 1, right, because it's a fraction, right? And then we might have some other constraints on our allocation. A common one is that it has to be positive, so you can only have a positive number of a stock. This is called a long-only portfolio. Shorting is when you have a negative amount of a stock. And then we have this gamma, which trades off, this is a parameter here, it trades off risk and return. And we can see what this looks like. So this was a simulation with 10 different assets. And we have this green curve, which is the trade-off between risk and return. So you can see we go from, this is plotting return, right? How much my portfolio increases in value under some simulated model versus the standard deviation. So, right, under different realizations, how much variance is there. And so you can see as we increase the risk, as we increase the variance, we get more return, right? This is the classic risk-return trade-off. But it has an interesting shape because of this positivity constraint, right? It's not just a line. And then these red dots are what happens with if you just hold holding one asset for the 10 different assets. So you can see this optimization is doing something for us. And if we blow up 2 of these points on the risk-return trade-off, you can see it makes a lot of sense. So here, this green one, this is less risky, right? The expectation is more concentrated, or the probability is mass is more concentrated, versus the more risky one, it's less concentrated, right? It's fatter tails, but it has a slightly higher expectation. All right. Another example, power management. And again, this is something you can really use. This is actually at least how it should work in theory. In practice, it's not quite this nice, but I think they could do this if they wanted. So here, imagine you have a bunch of different devices, like generators, loads, meaning things that use power, storage systems, like batteries, thermal, HVAC. So these you can vary, for example, how much, what level the air conditioning is on if like power is really expensive. Transmissions lines, those lose some power. So you just have these different devices, and they each have objective functions and constraints, like how much energy the power generator can produce, and then how much it's costing to run the generator. That would be the objective and the constraints. So you just give them all objective and constraints, and you just make them convex, and then you connect the devices sort of at, I think we call them terminals, with these nets. So these are sort of ideal wires. So they conserve power. So if power goes in, the power comes out, right? And then you can just aggregate everything, just sum everything together, do dot solve, and then you get your power grid, planning. So you could also incorporate time horizons into this. So you need to do that really to use the battery. It doesn't make too much sense to just, right? To really think about using a battery, you have to have some prediction of how the power is going to be used, at least over the course of the day. And so you end up getting this sort of a control problem because you're managing all these different resources with some expectation of what's going to be needed and some planning into the future. And actually, you also get from this prices. These are real. These are part of how the grid is managed. They're called locational marginal prices. It's just how much the power should be charged, how much you should charge for the power at the different locations. And so here you can see a little visualization. So we have 3 devices here, a generator, a battery, and then a load. And they're connected by a net. So this is meaning just this ideal wire, right? So that's this little dot here. And you can see that this is the planning horizon for these different devices. So you can see we are planning to, so this is how much energy how much power we're going to sink into these different things. So the load is going to use a certain amount at the beginning of, say, the day, and then it's going to use less, more, less, then a lot. The battery is being used, charged and discharged. So negative is being discharged and positive is being charged. And then the generator is always providing power, but it sort of varies. And you can see that we were able to, so we had a lot of load demand here, right? But we're not actually, oh no, we are using our generator a lot. Well, you can see the generator and the battery are working together to supply this load. And then this price, this is the locational marginal price right here. So it's basically how much everybody should be paying for power. And you can do a cool thing where like the generator pays the battery or the load pays the generator and the battery sometimes is paying money and sometimes making money. Anyway, you can do fun stuff with this. And we did this in a object-oriented way. So we just have different classes that sort of have in their constructors, they have objective functions and constraints, where you just give them a few variables or a few inputs, and then they construct everything. And so here you have like the load, you have a generator, you have storage, and then you connect them all. You make this network, and then you do .optimize, which is essentially just summing everything and calling .solve. Again, no, you don't say anything about what algorithm is being used. Like we consider that our business as the experts at Convex Optimization. As the users, you should not need to know anything about that, just like you have no idea how the compiler is compiling, right? And then, yeah, you can get the prices. So in summary, the main takeaways here that I hope you leave with is that Convex Optimization is something you can do easily with CVXPY. There's a lot more material on this on our website, cvxpy.org. There's a nice tutorial. There's a little short course that goes through this in more at a bit slower pace and more detail, lots of examples. We have some other packages that build on CVXPY at this GitHub group, looking at different domains and sort of non-convex problems. Thank you.
We have time for a few questions.
Yeah, just anybody.
Yep.
Yeah, or you.
So CVXPy is awesome, and everybody should try it. It's really great, especially if you like globally optimal solutions. It's good. But question is, so after CVXPy canonicalizes everything, is there some way, or have you thought of some way of freezing that or like caching it? So if you want to do a bunch of solutions really fast.
Yeah. So we were working on code gen, and it's actually almost there. OSQP, which is a QP solver, it actually has code gen. So if you're solving, and we've been trying to sort of bring that up the stack. Another student, Nick, I think has it working or almost has it working. And so hopefully we'll get that out at some point. And so then, yeah, you can use it for things like control problems where, yeah. Yeah, go ahead.
There's also a mic there in case you want to step there.
I think the main question is, you mentioned A and B can be NumPy arrays. Can they be something like, well, sparse arrays, that's one obvious question. The other is structured array. I know it's a diagonal plus one rank update. Can I specify that somehow to a solver?
Yeah, that's a good question. So they can be sparse. They can be, in terms of structured, there was another sort of package that I did which was more focused on structured linear operators and trying to sort of generate solvers in some sense that were exploiting that. For a lot of cases, like the one you described, you can get all the advantages if you just sort of express things correctly. But that is an area that we're trying to bring more into the main package.
Okay, and I also hope you could say a few words as to what is available to a user sort of out of the box. Say I'm on Windows, can I use your solver, I mean, CVXPY comes with certain solvers.
Yeah, they should be installable anywhere you can install CVXPY. You can install it on Windows, so you can use it on Windows. Yeah, somebody out there?
All right. My question is related to the previous two. Like I noticed, like some it's about solver optimizations. I noticed on one of your slides you mentioned you had a warm start. Is that a feature for CVXPY now? Or?
Yeah. So that's a new one we added.
Awesome.
Let me go to that. So we had a big update, which I didn't really talk about, but there's a lot of new stuff in the last. I think we pushed that out about a month ago, including Warmstarts. So particularly for QPs. It caches a lot of things now, and so that can be advantageous. And so essentially, if you're solving the problem multiple times with different parameter values, like in this case, you have everything's the same except for this gamma, then in theory, the work of solving the new problem will be minimal, will be much less.
And I know your group has written a bunch of specialized solvers that take advantage of the linear algebra structure and Warmstarts and stuff. Have you, is anyone in your group converting some of that old C++ code to Python or?
Yeah, well, we did, I wrote something for structured linear operators, and it does connect to CVXPY. There were some more algorithmic issues, you could say, or robustness issues primarily. I think that's a really big thing with actually deploying these solvers is robustness. It's sort of underappreciated. It's not easy to make them really work for all the crazy problems people throw at them. All right, well.
Oh, okay. So I'll just let them set up and you could.
Oh, okay,
some
great.
questions.
Yeah, there are more questions. It would be great.
But if you can just.
Oh, okay.
Yeah, you can go ahead and ask. I think.
I have one question. Are there any restrictions on use outside of academic with the commercial solvers you mentioned? Are there license restrictions on it? It has a different license.
So it's all Apache 2 essentially with the solvers that are built in, and so that should be no issue. With the commercial solvers, which are quite good actually in many cases, and worth looking at. They usually have academic license. I think they all do. So that should be possible.
But for someone some commercial user who has licenses for Groby, say, you can use CVXOpt without it. Is there a different license you have to get? Or you can just
No, there's no different license. No. There's if you have the solver, you can use the solver. There's nothing else.
Thanks.
Yeah.
So I've used CVXPY quite a bit. Just want to say thank you very much.
Oh,
That's awesome.
thanks so much.
I did want to ask about the 1.0 release, maybe just some notable differences, and then maybe future plans as well.
Yeah, so that one was really fun. The biggest difference was on the inside. We basically, so it was the way it worked before, it's like a compiler, right? And it basically had sort of one way of converting the problems to standard form, like one method of compilation built into it. And so everything was sort of organized around this one particular way of doing it. But we made it more like LLVM, where there's just different things you can do to the problem, like different passes, and you just link them up, and that gets you to the final form. And so this made it easier to have QPs versus cone programs, and in theory, many more things. I think there's a lot more we can do with that. So that's one area. For example, can you rewrite a problem to make it easier to solve, or better conditioned, or something like that? The cogen thing, that's a feature that I would really like to have in there that hopefully will make it in.
Thank you.
Okay, well, thanks so much.
Thank you very much.